What is the subject of study of the pharmaceutical or medicinal chemistry? It is exactly the same. It is a synonym. In some texts, it says chemistry pharmacy. It is the same. Here are three definitions. The medicinal chemistry says, for example, the definition of Patrick. It is the design and synthesis of new drugs based on the understanding of how they act at a molecular level. A useful drug must interact with a molecular target in the body, that is, what is called pharmacodynamics, and be able to achieve that target or pharmacokinetics. So there are two important concepts. The concept of pharmacodynamics, which tells us or describes how the interaction linking receptor is, and the pharmacokinetics that describes the molecule itself. And we are going to abbreviate all pharmacokinetics with this acronym. And we are also going to add the prefix tox. What does that mean? Yes, perfect, right? It could be absorption, distribution, metabolism, excretion, and toxicity, which have to do more with the chemical structure of the compound itself, as well as how it is metabolized at the hepatic level, for example. An official definition of UPAC says, the medicinal chemistry is concerned with the discovery, development, identification, and interpretation of the action mode of biologically active compounds at a molecular level. Again then, at a molecular level. That is why we stop so much in intermolecular interactions, which I hope you are reviewing, retaining those values, those distinct amino acids. It is important. And finally, a definition from an author of texts of medicinal. He says that the medicinal chemistry is responsible for the isolation when it is a natural product, the characterization, and that is, it is a broader definition. Yes, of course, we could also mention that the semisynthesis or the emisynthesis is included. Yes, of course, we could also mention that the semisynthesis or the emisynthesis is included. From a natural compound, we can obtain something relevant. Example, in the past, from the... There is a fungus that comes out of the rye, which is a wheat, right? And that alkaloid, that fungus, produces, and from that fungus, from the rye, which I think is later, I have an example of that. From that fungus, compounds called ergotamines are extracted. Exactly. But from this, or those ergotamines, by acid hydrolysis, lysergic acid is obtained. And that then, by amination, a molecule called LSD, or lysergic acid diethylamide, is obtained, which is an hallucinogenic drug. Now, LSD, as such, was studied at the time for the treatment of depression. In other words, it was not to produce a hallucinogen and sell it, but to study drugs for depression to cheer up. But it showed that it was a powerful hallucinogen, and therefore it could not be a drug. So this is a classic example of an emisynthesis. Of something very complicated, like an ergotamine, something simpler is obtained, like the famous LSD or other derivatives. I already have an example. Then you will say, well, today we are going to see several pharmacophores, and I want you to retain the chemical pharmacophores that we are going to see. In other words, today's goal is that, as it forces them to learn amino acids, today they are going to be forced to retain certain structures of drugs, which are the basis for different families of drugs. So here we have an image that shows us that medical chemistry is a multidisciplinary discipline. That, on the one hand, we have to synthesize the molecules, test them biologically, and then interpret their mechanism of action. For example, we can start here. In the laboratory, we start here. In any part, one can start. But for example, without the desire to be self-referring, tend to occupy these tools first to save time. And if something goes more or less well here, we risk synthesizing. Now, what is the great end of this whole cycle? Ideally, obtain molecules in the nanomolar range. Here, we have two ranges. When you get something micromolar, that's just a hit. But if it goes to nanomolar, if it is a leader compound, well, finally, we aspire to have something nanomolar. That is our great goal. Something with nanomolar affinity. So when I say nanomolar, I mean the affinity for the target. Now you will say, for something to be a drug, it is a requirement that it always has nanomolar affinity. Not necessarily, but it is desirable. Not necessarily, but you will say, why is it desirable? Because if something has nanomolar affinity, it means that it is more selective. So with a nanomolar affinity, it improves our selectivity. And if the selectivity improves, it means that there is less. Eventually, there is less toxicity and less adverse effects for affinity with other targets. Question: can we get to something even more powerful than nanomolar? Because how much is nanomolar? A nanomolar is equal to 10 raised to? Very well. Minus 9 molar. Already perfect. Then you can see here. A molar peak would be equal to 10 raised to minus. Perfect. Minus 12. Very few drugs have managed to reach that rank. Very few. It is very difficult. You will say, but it can be. In fact, it is not only possible, but it is a requirement for the development of modern antivirals. For example, anti-B, anti-B, or anti-Hib drugs have to be in the range of 10 raised to minus 12. Why? Because they are very toxic molecules. That is, you have to minimize the amount that is used. And since the patient has to consume that for life, although the disease, it has to be something that hopefully minimizes adverse effects because those drugs cause dementia. Sooner or later, they will damage the brain. But at a practical level, most drugs are only here in the nanomolar range. What is then? Says here, the subject of study of the pharmaceutical or medical. The subject of study is the drug in the molecular, chemical, and structural in such a way as to relate the chemical structure with the biological activity that it has. And here we are going into something that from there we are also going to invest doing workshop of this, of what is called KUS. No one here is going to come out with only theoretical knowledge of this, but we are going to take it to the empirical, experimental plane. So, although this is done at a the ultimate goal of medical chemistry is to find relationships of structure-activity. Of its acronym in English, structural activity relation. So what we want are two things. This are, which is qualitative, and the CASA, which is quantitative. So we want to find qualitative relationships that we can represent graphically. Or we can create a diagram of bars, something simple. Or we can find a mathematical equation. Finally, when we talk about Cuisera, you are going to be able to build an equation. I am going to pass you some databases plans with which we are going to work, and you are going to have to bring a notebook to be able to carry out those sessions. Example, here we have a SA, and this SA is qualitative. It is a molecule designed with a certain activity that you are going to learn pharmacophore. And you are going to be able to tell me question. Let's see if you had to remember the amino acids. Let's see. Be careful. Look first. There is no problem, but look. That nucleus that is there, it was too dark. That nucleus that is there. What amino acid does it remind you of? Sorry, what thing, histidine? And if it was the fifth, maybe. But tryptophan, very well. Then it looks a lot like tryptophan. That's why I tell you, now we are going to start learning pharmacology structures. And it turns out that a key neurotransmitter at the cerebral level is the following. Well, this is going to be protonated to pH 7, and I have that this is position 1, 2, 3, then this is the fourth, and this here is the fifth, and there in position 5. This has a... Does anyone recognize this molecule, or is this familiar? Be careful, GABA was acid, gamma-aminate butyric, but they brought something closer. It is at the cerebral level. Very well. This is serotonin, or 5-hydroxytryptamine, or serotonin. And serotonin is the neurotransmitter in charge of regulating mood states. Therefore, seeing this structure, you will say, this has the serotonin pharmacophore. Because if we continue to mark the molecule, see that later, we have 2 carbons and a nitrogen. The same here, 2 carbons and a nitrogen. So you see the structural similarity, already the ring. What is only the heterocycle? What is the name? I'm going to give you a data. It starts with I. Indazole or indole. Indole. It is an indole. So this nucleus is here. The pharmacophore was hidden inside the chemical structure. And you've seen, this will conclude that this molecule is a serotonin molecule. Serotoninergica? Yes, it is a compound with serotoninergical activity. How many serotonin receptors exist? So far, the following receptors have been discovered. 5H. There are perhaps in quantity. I have not counted them, but we have from 5I1 to 5,7. And within them, there are subtypes. Not in all families. For example, 5I3 is only one type because it is ionic channel. But within it, there are subtypes. So, having 7 large types of serotonin receptors, the question is, and this in particular, well, this was agonist 5I6. Well, the thing is that if you see around it, there is a structure-activity relationship that was found after a study, and that says that it can be done and cannot be done. So, for example, it says here that this ring that is connected in green, it says piperacin, is better than more. It is better for what? For biological activity. So there is piperacin. Question. Which of the 2 nitrogens is the basic one that is going to protonate to pH 7? Very good. The bottom one, perfect. Because the top one is conjugated. The top one, instead, this one is going to protonate. And we are very good. Other things, for example, here there is an alcohol, a hydroxyl. It says other groups of hydrogen bridge acceptors could be explored. Either another group could be placed capable of receiving an electronic pair or simply have a carbonylus here, etc. So that is a structure-activity relationship that you are going to find through an equation, through a mathematical equation. Very good. Let's go to the next one. And what are those equations that you are going to obtain? They are as follows. Here I have an example with several molecules. This is nothing more than illustrative. It says here, chemistry library. If you look, there is a set of molecules. Now, how many molecules are going to be necessary? That when we get to the equation, how many molecules are we going? Well, as what one wants to build a line, theoretically, if we want to build a line, how many points do we need? Well, if we have 2 points, it gives us an R of 1, then at least 3 points. But since 3 points is it is said that to build an equation we need about 10 compounds or more. From there up. Ideally, more than 10. How many? Against more compounds, better. There is no limit. It can be 20, 30, 100, 500. Against more compounds we have, better. Then we need a large library of compounds if I'm going to pass you a grid. Obviously not with 500 compounds, because we need to do it within the module. Then it will be a quantity that you can handle in the time that the classes will give us. And then, when you have the molecules, this question is asked. They're going to order 2 things. What biological activity do you have? What is the biological activity? And therefore, here you are going to transform, create a column, report the pick 50. Do you remember what that P was? Yes. Very well. That was less logarithm. Very well, of the I50. To be able to transform, to be able to obtain the P, we first needed to take this to molar scale. And on the other hand, they are going to calculate. And I say calculate because we are not going to empirically determine the physical properties of the compound. Obviously, for reasons of time, and nowadays no one takes the trouble of calculating each molecule, of determining, so that if we can calculate, and it is much faster, and the equations are quite good, then you are going to calculate for each molecule, and we can automate it. I am going to show you how. We are going to optimize this. We are going to determine the psychochemical properties. Well, here there are 2 things. Let's see. When we say physical chemical properties, also on the other hand, we could have as descriptors what is called fragments simply. Okay, molecular fragments, and then we are going to have that. You are going to correlate in a multilinear regression equation the fragments or the properties with the P and the IC50, and you are going to obtain equations. So, what is this here? What is it? It is a multilinear regression equation. How can they get that? For example, in a simple Excel, they can go to an Excel. They can go to another. What program are they going to use? Well, they are going to have to download the following software. Look, I'm going to open it. Give me a second to see if I can connect. Well, one of the programs that will serve us to calculate descriptors for free is called paddle descriptors. Let's see if we can find directly here the website for the download. Yes, paddle descriptors. This program, in a quick way, allows you to calculate. This is an online calculator. No, we need the program, because there you are going to generate an output file with thousands of files. And then you're going to have to go to the paddle descriptors, and then you are going to have to go to the paddle descriptors, the program, because there you are going to generate an output file with thousands of descriptors. For example, here it says, Generates self-correlation descriptors 346, generates constitutive descriptors 120, generates molecular properties 15, generates quantum descriptors 6, etc. I'm going to send you a link so you can download it because a line like this is not going to serve us. Yes. Tell me where the line had. This, it will be quantum. I think that maybe it was what I saw. There is no problem then. This program is free. If you find it first, well, if not, I'm going to send you a link. And second, apart from this program, they will simply need something where to do multilinear regression. And there we have from simple Excel or a program called SPS to do multilinear regression calculations. It also serves a program called statistics. And any of those programs serve to do multilinear regression. They are quite practical, easy to use. If you want to work with Excel, we can also do it. It is also possible, I think, that you have to enable an option, or I do not know if the new Excel will bring it by default. Okay, good. Then we go back to focus only on the tip. Well then, we have these concepts. We already know that in English pharmacy and drugs are synonyms. Okay, oh, this is drugs. But we in Spanish make this distinction between pharmacy, which is the same as the active principle. That is, the pure molecule versus drugs, that is something negative. Pharmacist form is ready for its final dispensation, and we also have the concept of DZ or common international denomination for several of these pharmacies, which is a way to systematize the names by avoiding using the names JUPAD, and we had already defined what Admetox was good. Regarding the common international denomination, it uses prefixes and suffixes to help us identify. Drugs example, look, if I tell you propranolol, etanolol, perfect, pindolol, etc., then note that we are using a suffix that is the same in all cases, and when you see that suffix, they say that is an antihypertensive. That is, specifically speaking, it is a beta blocker. A drug for the treatment of arterial hypertension. I am going to send you a list, or if it will not be necessary. Where are the main common international denominations of today's pharmacies? There are many, but there is a list with... Well, here I have some quotes a little funny already from this philosopher. Voltaire says that doctors administer pharmacies, of which they know little to cure diseases, of which they know human beings than those who do not know anything then. It is quite funny, the quote from Voltaire. Well, it says here that the pharmacies are normally composed of low molecular weight that interact with macromolecular targets. Now it says here they are normally low molecular weight. Is it always like that? No, it is not true, because there are pharmacies of high molecular weight. If we have pharmacies of high molecular weight, for example, the monoclonal antibodies. What is the point there? That they must be administered by intravenous route. Because by oral route, they are going to be degraded by the digestive enzymes, and then that have a peptide type structure are not active by oral route. They must be injected. Very large molecules must be injected. Okay, then we are going to see now some ways to give name to the drugs. There are more definitions. We are going to name the drug. Well, things that you already know. Only to say that the number of identification of the chemical abstract service or case number is a number that identifies each existing molecule in the wrong way. Well, particularly organic molecules. Note the following. They already have the total amount. I do not know if the total amount comes out there. For example, here in ChemSpy indexed, there are 64 million chemical structures, and how many new ones every day are reported? About 12,000 new compounds every day. The case number is a number that identifies each molecule in the wrong way, and in these databases, you can find the case number, you can find the structure properties, and the provider that sells these molecules. And ask this compound is going to be administered by oral route or intravenous route. Very well. What do you think is the common international denomination, the top or the bottom? Very well. Then here below is the common international denomination. Above, what is this? The name you pack? Third, regarding the chemical structure, what is the pharmacophore, that is, which part of the molecule is responsible for biological activity? This is a drug used for the treatment of autoimmune diseases, such as lupus. Then, what we want is somehow that reaches the genetic material and generates a change by stopping the activity of the immune system at the genetic level. Then, what will be the pharmacophore? And well, then we did not ended up with proteins. We did not see nucleic acids. But what? And that is, they are nitrogen bases. It is not true. It is a sequence of nucleotides, and then we have that this is the pharmacophore that is repeated 4 times in the molecule, all the way. Rest are connectors that will happen with this, as it is called, that type of link. Very well, we have a phosphodiester link, and that link is going to break when this reaches the cells. There will be a break, and that fragment will be inserted in the genetic material. There will be an expression or a suppression of certain genes. Then the phosphodiester links are broken. They are hydrolyzed. Second example. Fungina. All those who end up in fungina are a specific type of antifungals to kill fungi. That they can tell me about this molecule up to the name of Jupac. Serves to kill fungi. If we go to the chemical structure fungin anidule, there we have there. There you see how important the DSI is, so as not to be giving it a Jupac. Simplified, simply a term. And the drug, this part of here, that is what it is, of what type you have already seen biomolecules in some parts. Look to see what happens with this. I know that. This molecule is a bit strange because it looks circular, and in reality this is folded in space. Each vertex is an atom here, for example. It is a carbon. Look at the next exercise I am going to maximize here, and there is the thing here. I have a carbonyl, and here I have an amino, and in the middle there is an alpha carbon. Then that is an amino acid that is connected peptidically with, for example, here with the hydroxyproline, where we have amino, that is here. There is another alpha carbon that has an amino and a carbonyl, and this vasoproline. But as it is hydroxylated, it is a hydroxyproline. Another time then, we are going to mark. Then we have another alpha carbon here. Then we have again a certain one here. And there it is over. Because it turns out that this one here is not, because there is no side or lightning. And there, but this one here, if that, How many amino acids does it have? Then it has 6. Very well. It has 6 amino acids. Perfect. We have 6 amino acids. Sorry, the abbreviation would be double 6 amino acids and the peptidic links. How many? Already. Very well, the peptidic links, there's one good this here. 2, 3, 4, 5, since for the other side, remember that this is not true here, it ends. And this piece here is not an amino acid. It is already a common. This is actually an aminal. It has a carbon with an alcohol and an amino at the same time. So there are only 5 peptidic, probably such. 1, 2, 3, 4, 5 peptidic links. It is a measure, but peptidic link, because what there is for the other side is not an amino acid. And that is links explain then how we can see interesting things already when we see the chemical structure. Now, I could also ask you a question that a complex. What is the ionization state of this pH 7 molecule? Because it is so important, because when you do docking, the molecule has to be neutral charged, and that is determined. This will be neutral or charged. That you can tell me to see all this part so complex, the triphenyl part is neutral. And then we forget about that and maximize the rest. Remember some values. I'm going to give you some values, but you should know how much A is the pKa of an alcohol of 16, for example. This alcohol of here, pKa 16, already closer, and a phenol pKa closer to 10. And now it can be less depending on the environment, therefore pH 7 will be neutral. Our neutral pH 7 alcohols, there is some other ionizable group. There is an acid in the structure or a free base in the structure. It is very interesting, despite the fact that it is full of functional groups. It does not have ionizable groups. It is 100% neutral to pH 7. I do not see any, because for the other side, notice this is an amide and this here is also an amide. So it will not be protonated, and those that are part of the peptidic bond are not amides either. So interestingly, this complex molecule has a net 0 pH physiological charge. Let's see another example. And when one sees this type of structures again in Pharmacophore, to see if they are implying, then remember in the first class, how is the long-term memory perfect? B, beta-lactamic. What is that? Then, because it is an antibiotic, this type of structure destroys bacteria specifically when we have that the beta-lactamic system is connected to a thiazine. This is a porine cephalosporin. And all the porine cephalosporins begin with if they have a prefix, the same prefix ceph. Cephmetylenum, well, this is already uncomfortable, because this type of wounds that occur in the skin are caused by a fairly difficult bacteria to eradicate a staphylococcus that infiltrate under the tissue and produces these tremendous, since they are super painful and burned with something, with a kind of hot metal to sterilize. But imagine how they are going to do that to this baby who has a full face. And that is because the guavas, when they eat, you have to wash their face, not to give them a little cloth. Because if the bacteria are not there, they are reproduced, and they are a super painful crust. More of something like when you were a child. And you know how painful this is, and it is fought with antibiotics. It does not serve a cream. No, The antibiotic has to reach the bloodstream. Well, we go to the chemical structure then. Whenever you see this famous ring, you say that it is cytotoxic. It is probably antibacterial. Well, we are going to the structure now, how it will be to pH 7. This is the name of the structure now. How it will be this to pH 7. There is some ionizable group. And very well, I am going to erase here. And the acid then, the acid to pH 7 is going to be with negative charge something else. This is amide, this is imine. But the amines are not very basic. This is an sp2 nitrogen. Also has the attractor effect of an oxygen, less basic, still does not protonate it. And this, because it is not very basic, because it is 100% conjugated by resonance in this aromatic system, so neither, and this is a nitrogen sp2, is not basic. System is not basic to me. It does not have a neutral amide, neutral imine. This is not basic. And this, what is this? What is the name of the ring? Perfect triazole. Well, and the triazole that goes to pH 7 is protonated or deprotonated, is base or acid. Well, it is an acid. It releases the proton to pH 7. It has a negative charge. It has a pK SWAT around 5 or even a little less, due to the sulfur effect, since it is not very conjugated by resonance by the size, but rather prime, its inductive effect, so we have charge net minus 2 pH 7. Okay. That would be with respect to this particular compound very interesting. Ionization state. I was also trying to remember part of the mechanism of action of molecules in some of these compounds. All this group is an outgoing group of the structure. But here it remains connected here. It does not act as an outgoing group. Well, and finally, if you want one more that is relevant here, we have two more. These are much simpler. And with these, I finish this part of the tip. It says here, the name Jubacdisti, diclofenac, OK and AKO. This is an AINE, that is, it is an anti-inflammatory non-steroidal, that is. The structure is not that of a steroid, but of a conventional organic molecule. It has a carboxylic acid that will be negative to pH 7, and instead the molecule below has another pharmacophore does not have this pharmacophore of carboxylic acid connected to a benzene. This is a pharmacophore of type aryl, that is, we have a benzene ring or naphthalene. In this case, aryl. Aromatic oxypropanoamine that is typical of beta blockers agents. In fact, here, below it says beta adrenergic blocker, a pharmacophore of type aryl oxypropanyl amine will give the same chirality of this hydroxylo. No, it does not give the same chirality of the hydroxy. Okay, there is always an enantiomer that is more active than another. The enantiomer that the most active enantiomer is called, remember the name? The most active is called is the enantiomer with greater biological activity. There is always one that is prime in terms of off activity, or sometimes one can be inoculated and the other can be toxic. They have heard about the thalidomide structure. Let's see what is the structure of the thalidomide. Here they are in RS, a central chiral mark the difference between a drug that eliminated nausea and pregnancy discomfort versus another enantiomer that produced mutagenia. That is, changing the genes making babies born without arms, without legs. See how terrible. Only by a central chiral that marked the difference, so a central chiral can be for good or for bad. This is already drastic at the biological level mixture. If they had known before, obviously, they would have sold only one in enantiomer, but they sold it as the mixture because it is also expensive. It can be done, but it is expensive. Enantiomas, okay, we go back to our note. And what we are going to do now is go to the next note that is of relationship structure activity. If you give me a second to move to the next note. We were here where the other is here. Okay, drug search methods, I think we have not. And then we have seen several structures are retaining those structural motives that we have been seeing. We are going to move now to the following progress in drug search. Number 1, the drugs. We are going to classify them into two great types of unspecified action or specific action question. If we go here to see what happens there with that person that is anesthesia. These are 4 historical anesthetics. They no longer occupy precisely these same molecules due to their toxicity. For example, the diethylether accumulates in added chloroform and the allotin are pathotoxic. The nitrous oxide produces a very strong dilatation glass. And apart from that, it is an agent that produces as an adverse effect, you know what the strange adverse effect, that the nitrous oxide produces uncontrolled laughter, very strange, as to throw it on a birthday so well. All these molecules question, they have something in common. The truth is that not much they are small molecules where there is not a pharmacophore, that they are repeated, all of them, and in that case we talk about an unspecified action because they do not act on a particular protein target. Yeah. There is no target protein in which they are acting. There is no membrane receptor, an enzyme in which they act, but they act. And what do you think they do, these molecules? Because, for there is a general anesthetic effect, they must act on the brain. So what do you think you do at the level? Yes, exactly. They produce a disturbance in the transmission of the nerve impulse. They are molecules of high lipophilia. They have what medium descriptor, the lipophilia. Already the P, they have a high log P, very well. And what they produce is an alteration of the neuronal membrane. And they produce an alteration of the neuronal membrane. Instead, here, within the multiples of example here, will be most of the times what we be seeing a specific action pharmacist, when there is a protein in which it acts if there is a target. If we have a target, and that target is going to be some protein, or it can eventually even be genetic material, and the specific ones have some pharmacophore in common, well, Here we have two pharmacophores. The pharmacophore of an antibacterial sulfate and the pharmacophore of an anhydrous carbonic acid inhibitor or acetylzolamide. The first is an antibacterial agent. The second is a diuretic agent. The antibacterial agent, the sulfate, what it does is imitate, and we saw this in the past. This fragment imitates the benzoic amino acid that the bacteria occupies to synthesize. A cofactor in the synthesis of genetic material, here it is this, that you see here is the bacterial. Folic acid and the bacteria occupies three things, or to synthesize the folic acid occupies or acid for benzoic amino, there it is. And on the other side, it is not true what we have on the right. This is an amino acid, which is the one that had the long chain, the aspartate or the glutamate. If this is glutamate, very well. Then we have a fragment of glutamate, we have PAVA, and we have a heterocyclic molecule called pyridine, which is all this down here. So the bacteria assembles those three fragments, and we give origin to the bacterial folic acid. But if we give it the sulfur, the bacteria in the sulfur competes with this, and therefore it cannot assemble the folic acid. Look at the tremendous similarity, retain that structure of that portion. With this then, here it is a pavacid amino, not true. And instead here of the acid that we have, instead of the acid, a sulfonamide, and this sulfonamide releases a proton equal to the acid. Remember, how is the memory of the medium term? When we saw pK2, this type of compound, we did a lot of questions like a workshop where we calculate pK2, the pK2 of that proton 5, and we explained that it comes out because apart from the sulfur is an electric attractor, it has an electric attractor ring on the other side, and that proton comes out, it is released, it is lost to pH 7, and instead, the other is a diuretic. It no longer has the same fragment, that there is a significant difference. Is therefore an open book structure. And second question, another type of structures here, they have already been retaining things. So what? Can you tell me about the first two? Excellent. And therefore they are antibacterial, the same action mechanism. If they are antibacterial, question the one on the right. There is a generic name, but based on the structure you believe that this compound here has the same action mechanism as the first two. Very well, it does not have the same action mechanism. Structure of pharmacophore structure of the beta-lactamic type is very different. In fact, the tetracyclines, what they do is inhibit the protein synthesis. Inhibit the protein synthesis at ribosomal level. Instead, the first penicillin or porine cephalosporins, the beta-lactamics in general, they remember we exactly very well. If at the peptidoglycan level, very well, it prevents the peptidoglycan synthesis. They act at the external level of the bacteria. The tetracycline has to enter the bacteria today, quite in disuse, the tetracyclines, okay, because the tetracyclines, these very complex, rigid structures, so polycyclic, tend to be very passive. Toxic structures, very polycyclic, tend to be generally toxic. It is difficult for the organism to get rid of that molecule tank, and this type of structures produce phototoxicity on the one hand, that rejects light and also causes damage to bones and teeth. They cause damage to bones and teeth. They are clearly altered, as is altered there. Metabolism of calcium. They produce weakening of the bone and dental matrix structure. Most likely, yes, because notice that when one sees the structure, we have oxygen pairs of oxygen. When one has that, it turns out that the pairs of oxygen at that distance coordinate quite well with calcium +2, and if something is dragging the calcium of the bones of the teeth, it produces long-term weakening damage. Well, some observations about it, and that is what interests me, that throughout this course you can read a molecule the molecule is not hidden there, but that you say these are of natural origin because they are very complicated molecules with many chiral centers. Very well, then an indicator of natural origin is that they tend to be chiral centers. Second, it says present a different mechanism of action because you are now comparing pharmacophores. They tell you they are not similar to these molecules. They cannot have the same mechanism of action. Third, well, this is debatable already about the solubility. In reality, it will depend. If I manage to form a salt, for example, how I could form a salt in the penicillin. Perfect, then we can here form a salt. It will not be very soluble in reality. But, for example, we could form here a potassium salt, as I could form a salt of a tetracycline. Perfect. Very well there, and therefore we could have a chloride contraction. Then we can form in reality. That should say I have to rectify their more than solubility. Salts can be formed that improves the dispersion in the middle of the bone, because they are so big that I think they will not have 100% of solubility. Thing fourth, there are clear points of R. Metabolic degradation. Well, when we talk about metabolic degradation, break or cut, at a certain point, there are always 2 points that are critical. The esters can be cut, RON R2, and the amides, but they are more resistant, because the amides are more resistant than the esters. And we can cut there, okay, the conjugation of an amide is stronger, the electronic pair is more dislocated. I know more than the oxygen. The oxygen, I know less than the electronic pair. Remember that the oxygen is more electronegative. Then it is more difficult to break this link. It will always be more stable. Well, see some point of metabolic degradation based on what we have just said. For example, we can already break the amide in the penicillin. For example, the beta-lactamic system can be opened, and in fact, it opens, it breaks. And there is also a third, more difficult to see, that it is that the beta-lactamics have a particular degradation. The electronic pair on the nitrogen atom enriches the oxygen, then the result of that resonance. If now we draw a resonant form that is produced as a result of that movement, we are going to have that the oxygen, this is going to be positive. The oxygen is an electrophile or nucleophile. A nucleophile, that oxygen is very close to the oxygen of the carbon dioxide, and it attacks it, and the autohydrolysis occurs. This electronic pair goes up then it goes down, and then it breaks, capturing a proton of hydrogen water. Then it also has auto-hydrolysis. That is why the penicillin is not administered by oral route, because by oral route, that will happen. And now let's go to the other side. And here, there is an ester or something like that in this. Well, there is no ester, but there is an amida down here that could also be a point of view. Metabolic degradation. That is a type of reaction that can occur the breakage of an amide. In the past here in Chile, this type of thing was sold with deceitful advertising. The truth is that it is quite funny. It says here to improve. And well, it was used for everything. Coldness, discomfort. That is, when someone says discomfort, that is super wide. Of everything here next, also improve quick relief and compare it with the speed of a bullet and hunting an animal. In fact, somewhere here, it says that the relief comes seconds. Look there. It is compared with the speed of a bullet of 2 seconds. It says literally, it says 2 seconds after taking it, improves it, begins to produce impossible joy, because after 2 seconds of the compressed, it has not yet been added, so it cannot be, since after 2 seconds, there is an effect and the improvement. If I do not go to death, I think it was paracetamol. Caffeine in the composition does not come out here. Well, what is the timeline that we are going to go through? We have that since ancient times, medicinal plants have been occupied, of course, and the pure molecules began to be obtained isolated, produced on a large scale since about 1900. In advance here, we have the great discovery of Hoffman of aspirin. Then aspirin, a benzoic acid that is acetylated, that is, it is a salicylic acid, acetylated 1898. Almost at the same time the concept of the receptor was being discovered, Ehrlich said that there should be a protein or proteins in which these compounds interacted. 1945, that discovered Fleming very well. The discovery of penicillin in an accidental way in 1962. This was the last. The design of drugs exact. Of course, Hans and his proposal of equations to design drugs. Now, it was a step forward because for the first time it was proposed that mathematically it was possible to create a molecule, and not only by chemical eye, but mathematically. See what has happened? We have several important molecules I have here until 2012, and today with so much technology, it has been very difficult to produce new molecules, but great pharmacophores have already been discovered, which does not mean that today they are still looking for new molecules here. You identify several, I think. For example, if you are asked about the protein, says here, the protein is a local anesthetic, the morphine, a major narcotic, or analgesic here is the penicillin, antibiotic psychotropic chlordiazepine, that is, it is the father of diazepam, for example. Propranolol, the father of the beta blockers, urosamida, and captopril, an antihypertensive ranitidine, one of the first antacids. Are the most important families here? I skipped one. Fluoxetine, an antidepressant, omeprazole, anti-ulcerous, antiemetic acetone, losartan, antihypertensive, but by another mechanism, different antiviral therapy, antiviral therapy beta 3, adrenergic for urinary incontinence, or also these beta 3, such as miraviron, are selective fat burners. Why they fail? Why is it so difficult? Because despite the fact that one can create a nanomolar drug, they fail in red the alien. Pharmacokinetics, then one thing, is that the thing comes in a cell, but in an animal where the problem will probably be in the animal model. In the human model, the liver degrades it very quickly. Or there is another type of degradation. Then the main reason for the failure in the development of new drugs is a failure in pharmacokinetics. And how are you going to predict pharmacokinetics? I do not know if we enter a server in the past. It's a connection. Let's make a quick attempt. There was one of those that we could not enter the wall. Pharmacokinetics, you can evaluate it here. We see that. Now it lets us enter. And it says configuration you must use. I think it was that one. It is not true that we could not enter, but in a second, we are going to solve it immediately. We know that the university blocks this type of connections, so we are going to give it an alternative signal. Let's see. We could enter the other one maybe or not to the server of the Korea server. And here we are now. If the previous time we entered the Korean, the pre-admit, remember? And then a simple prediction of pharmacokinetics. On this website, we are going to draw some molecule that interests us, for example. It is like this, and I am going to place here a flower. We are going to place here the following question. What do you think this system is going to be? System here, something is missing. And this system, you think it will be innocuous or toxic. Small molecule, it is no longer a large molecule here. It says between, to see, wait. But if maybe I squeeze, I am not going to squeeze anything yet. First, I want you to tell me, based on the chemical structure that you believe that will be innocuous or toxic. Innocuous, because it is small well. It is certainly a small molecule. But look, more than the issue of football. I cannot move it. Okay, we already left it there. But there are things that are generating certain alarms. In the first class we had seen that the use of functional groups of type nucleophile or strong electrophile, and the use of strong electrophile is avoided, which group is a strong electrophile. And there is an aldehyde. Very well. It is rare a pharmacy with aldehyde. There is practically no more. We have three options, phenol plur, or this system called Michael's acceptor, which is an unsaturated alpha-beta carbonyl. Very well, this system. The Michael's acceptor, very well asked. It is here in the beta position. It can be attacked by a protein and rent courageously. Let's go there to see if this thing now gives us the RAM, transformed it into the smile code, which we already talked about in the past. And let's quickly see the prediction. Here it is. For example, it says if we maximize this part. I don't know if I can. Well, I can't modify the image much. It is already within. What is flexibility, lipophilia, size, polarity, degree of solubility? But it says that insaturation here shows an alert. When it says insaturation, well, it is making an emphasis on non-aromatic insaturations, so it should draw attention to the algorithm that we have. This sector of Michael, what we were just talking about, is outside the radar type diagram. Second, we are now going to the log PP. I do not know if you can see the log PP calculation. There is lipophilia. Consensus here is the average value, so to speak, 1.78. How much was the maximum? 5. This is going to have absorption. By viral enough, it will be very good, as it is a surface. And all of you say small. Which descriptor sees the surface of these? that are here, because in fact it is not convenient that the molecules are gigantic. There is a limit perfect. TPSA, or topological polar surface, says 54 is fine, because a molecule with more than 140 already costs it to be absorbable. And this one has 54, so it is going to absorb quite well since we are going to expand here. See that? On the right side, it tells us some things like that this is going to be highly absorbable at the gastrointestinal level. It is also going to be a compound that is going to go through the hematoencephalic barrier. That is, it is going to reach substrata, it says, of P-glycoprotein P. That is, it is not a molecule intestinal level, or also by the hematoencephalic barrier. This is the drugs and does not inhibit hepatic enzymes. These are the hepatic cytochromes. It does not inhibit them. So there is no alarm regarding some interaction with another drug. Let's see this graph. And it seems that I showed them at some point. Remember what this was. We did not see it well. This graph has the log P, with a certain algorithm calculated here in the far x-axis and the surface in the x-axis. That is, the P versus the surface. The white values taught have been statistically seen, where, if the drug falls here, intestinal, and the yellow area is apart from being absorbed intestinal, it reaches the brain. It is a graph of cooked egg. It says here, with boiled egg, it is a hard egg split in half. It is not true. So there you have it. It stimulates the appetite, and it says, red color is not a glycoprotein substrata. The point of the drug says, there is the molecule is red color, will not be expelled by this protein that pulls the drugs out. So it is interesting. Nini, you can get a pretty good predatory pharmacokinetics. Let's go back to our point. Yes? Of course. If that is what we are going to see, we stop for a second here. A second. Medical chemistry. To clear already perfect. There is Bugracia. And there it is. It says Brink, okay. The name of the descriptor says alerts that were published in 2008 in the Chem by Brink et al. There are two alerts. It has the finger and it has an acceptor of Michael. Thank you very much, Antoni. It is excellent, and so it works. Show the alert, of course, good observation. But if not also clear, ignore this. I would say it happened already, but it is super toxic. So thanks, of course. Well, there, you can see how it is complemented on the one hand by applying these techniques, but knowing how to read a chemical structure sometimes. When people do not know much chemical structure, they simply trust each other. And if, for example, this was skipped or here I did not say creating something toxic already, well, for the search for a serial head, with this we are going to close the idea for today. It says here. What is done in general is either from traditional or historical methods, that is, either from the extraction of a natural source or from a rational or modern method through an equation or a docking, for example, that is, of molecular dynamics. And within the traditional or historical methods, we have two great families highlighted from the plants, or it is also very busy to remove marine algae today. We can extract alkaloids or terpenes here. Are the two great families? Ask, what is the difference? We also saw in previous class. And some idea if how it is like the central characteristic of an alkaloid, central characteristic of a terpene, because we differentiated in functional groups already. The alkaloids, well, they have positive nitrogen, that is, it can be protonated to B7, Then there is a nitrogen structura in an alkaloid instead, in a terpene, not the terpenes usually have greater lipophilia. The terpenes come from a substructural unit called, remember the brick with which the terpenes are made. It is called ESO. Isopre, isoprene. Actia. 1, 2, 3, 4, 5. That is the structure of the isoprene is the brick, and that is why the alkyl terpenes are molecules that are multiples of 5 carbon atoms, 1, 2, 3, 4, 5, multiples of 5. The terpenes, and there are also other derivatives of carbohydrates and things like that. And then we see some pharmacophores to finish today that I am interested in retaining this type of structure. For example, when we study opiates, the pharmacophore of an opiates. The following here is the morphine that is extracted from the Papaver somniferum, the plant, and the chemical structure of the morphine is this complex alkaloid cycle, but the pharmacophore is an aromatic ring separated at this specific distance, 1, 2, 3, of a positive nitrogen. Therefore, to create a narcotic, I do not need all that structure so complicated, but simply an aromatic ring, and we need 3 carbon. 1, this was quaternary, 2, 1, 2, 3, and the nitrogen A. Nitrogen tat is positive then. If you respect that an aromatic ring, a quaternary, including the 3 carbon of distance to a nitrogen, the molecule that you are going to create is going to be a narcotic if that pharmacophore is respected. Apart from morphine, other alkaloids are also extracted, such as papaverine, that have a dilating base effect. And see the similarity seeing this papaver molecule. That is a heterocyclic type, as it is called, this heterocyclic. It looks like it is not close, but it has 6 already. Be careful, this is isoquinoline. It looked like it was already good. It turns out that this compound gave rise to an antihythmic synthetic chemical drug called verapamil, and what is common in verapamil with papaverine that also has a stabilizing effect. Well, if one rotates a little, the verapamil, if we rotate the structure and call X to the connector that comes after the nitrogen, see how it looks. I do not know similarity. For example, here, the isoquinoline part, here it was. Then, here came it only a carbon, and this anisole type system, the same here, only that comes with a more complex connector with nitrile and other things, but it was, that is, there is a hidden structural pharmacophoore to the case of the papaverine. That is clear, if good observation. This is difficult to rotate. That is, these 2 links are rotatable. But it is a bit difficult for it to rotate due to the hysterical impediment offered by the cycles. Technically, they are rotatable, although with difficulty. Second, another alkaloid cocaine here is a small error. Look at the image. This has 2. Pass in front of the plane. It was not behind the back. It was easy. That is the structure of cocaine then. What is cocaine? Good in its beginnings. Cocaine was used, as someone knows well. Here's the problem now. It is used as a stimulant of the nervous system. But at some point in its beginnings, it was used as local anesthetic. It is the best local anesthetic that exists in fact, but for obvious reasons, it cannot continue to be used. But if you want to create a local anesthetic, observe the following. We do not need this alkaloid so complicated. We need to respect this, that distance of this polar connector that is here. There is an ester and aromatic ring. An ester at a certain distance of a protonable nitrogen. With that, we can create several E molecules. I do not know if it is here next to. And what does the distance respect? Then you see nitrogen at a certain distance from the ester and an aromatic ring. And here it is more or less relative, because what happens is that, look, when we compare with our cocaine, I do not count atoms, because as the structure is bicyclic, the distances shorten a lot, because it is like contorted in the space, contracted then in the one can measure the tridimensional distance, for example, of this oxygen atom. I can measure the distance from atom to atom, and if I have a certain tolerance margin or a average distance, then I can create a new anesthetic. And that is what we have here. The protein is natural, or synthesis of synthesis is much simpler. Okay, then this comes from a pava of a benzoic paramino acid, which was connected to this chain. Seeing the pharmacophore, knowing what the pharmacophore is, we can create something completely new. Third case, we are no longer here. It is the famous cornice, which is a fungus that comes out of the centenum. That is the truth is like a wheat, and this structure that comes out, this is a parasite. It is a contaminant fungus. Well, but the ancient cultures took this fungus, they macerated it through space-time, consuming that, and the truth is that from there they took out this type of structures. Then here we have that the ergotamine, for example, would be here with the ergocristine, would be with this isopropyl. That is, this type of super complex structures are very large lipophilic. Well, and it turns out that chemically they realized that they could simplify. If you break by hydrolysis, this, where is it going to break? Perfect. And the critical point here is here in the center. It is going to break there, and when that part is broken, they are going to have a carboxylic acid. And then the carboxylic acid, if they make it react by amidation, they can have a nitrogen with two chains to increase the lipophilia, so that it reaches the lipophilia brain. Then by amidation, I can go from acid to amide, and that is the one that is in the middle. There is LSD. It is exactly the same, that they blew away all the piece that is not responsible for the activity and left the pharmacist for now. You will say, why an amide and not an amine? What would happen if it were amine? Instead of amide, it would reach the brain, or it would cost more. Perfect. If it were amine, it would cost more to reach the brain. For how much we would have a Chi-7 positive charge. But since it is amide, it does easily reach the brain. It is more lipophilic, but it will still have a positive charge. Where? Which of the two nitrogens? Very well. And this one is not true. And then one can protrude. But since there is so much carbon, it is so lipophilic that it also crosses the hematon fact in the equilibrium. Remember that there is balance, and that small percentage that we were calculating in past classes is passing little by little to the brain. Ask what pharmacophore comes here in the LSD and in all these derivatives. Because look, here are all the molecules. Okay, here are all the molecules. What is the pharmacophore? Exactly then. That is what I was interested in. And how it is called. This starts with, and the indole, Very well. Then, because the pharmacophore was not only that two carbons from position 3 and a nitrogen atom, two carbons and the nitrogen atom C, it is repeated they are in all cases, and that if we compare now, down here there is the serotonin, the indole, and two carbons, and the nitrogen atom are two carbons only from distance, and the nitrogen atom was hidden. The pharmacophore in alcophore cases two carbons. There is 1 and 2, and the nitrogen atom protonable basic structure. So it has activity in multiple receptors of serotonin, the hallucinogenic LSD, that only today is used for experimental purposes, or when one a drug with another to compare who has more affinity. And here they have it. There's the famous Dutch painter Escher, who, as far as it is known, could compose this type of paintings by drugging themselves with LSD that they have of rare. Rare thing is that the water goes up and down at the same time, or here, that they all realize that they are always going up or they are always going down, then impossible geometry. They say that I would see them under the effects of LSD. And the last thing to finish off. Now, we have here the alkaloids of the curare, which is a plant that in the Amazon with Semacera saliva. It heats up, they spread a dart, they place it there, weapon, and in that way they hunt the food. And then what it produces is muscle paralysis. We go to the structure with this, we finish. What is toxic about that plant? This and super difficult is not true. The structure is complex. The structure has two nitrogens, which of the two is always positive, the one above, the one below, very well. The one above, because it is quaternary, the one below is protonated, two positive loads, a large structure. There is a certain distance from this nitrogen to that nitrogen there. It turns out that this type of structure is joined to the nicotine channels. Exactly, the nicotine channels are the ones in charge of producing muscle contraction. Well, next to it, we have the acetylcholine neurotransmitter, which is the neurotransmitter that acts in the nicotine, channels the neurotransmitter, acetylcholine. You will say, and what is it like to give your curare to the nicotine? It is very little, only in one thing. Perfect, we have a positive quaternary amino, just like this one here. That group, in fact, is key for the acetylcholine to be linked to the receptors. Here is the most stable conformation of the acetylcholine, but what matters is that the acetylcholine way here is here. We have the nicotine channel, which is a channel for sodium and for calcium, and two acetylcholine are joined separately, of course one to each subunit. And when the acetylcholine are joined, what happens? The pore opens and calcium enters with sodium. Well, when something allows the step of calcium, the calcium inside the muscle cell produces the contraction, and then for that, this channel, so that the ions enter and fulfill their purpose well. The point is, arrives okay. What is going to happen? This is going to expand, but to acetylcholine. Well, what happens is that your curare is so large, the chemical structure, that a nitrogen is joined to a sieve, and the other nitrogen to the other site, preventing it from linking and producing a flaccid muscle paralysis. Then the pharmacophore is hidden, and then, based on that, people said, this is very complicated, and they create, sorry, that is what things are pesticides. Of course there is experience, of course, because if it is with us, relaxation, it is this type of structure in which they used to produce respiratory blockage to. be able to intubate people well. Someone said this is too complicated, very expensive to synthesize, but what happens? They measured the distance and said, they did this quaternary nitrogen with 3 methyls. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, nitrogen. And what do you think your activity? That is that there, they have the decametonium. That if it is a drug and a certain distance was enough, and 2 positive nitrogens, and it had the same if the one of your Curie, because we extract the pharmacophore within the most complex structure.